All right, now that we've established a few boundaries here, we know the period and things in terms of the time and velocity. Let's compare a couple situations here. All right, now in our situation number one, we've got a police car, and that police car or ambulance is sitting there, and it's not moving. So, as the siren puts out these sounds frequently, 1,000 hertz for example, and a certain amount of time between each one, the sound itself is being made in a very specific manner. So, we'll make a sound like, hey, 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 hey. Now, when the sound travels, the person at the other end is always going to hear that sound the same periodic time, because as the sound travels from here, that distance between people never ever changes. So if I stood here, every time I heard the word hey, say put your hand up, you'd put your hand up like this each and every time, just like so. All right, now let's change the game a little bit. Do police cars and ambulances move? And the answer is they sure do. All right, now if we have our source of sound and we put out a wave, the wave starts to travel. So we start out like this. The police car or whatever says, hey. The wave travels through the air like so, and it's actually in motion exactly like the wave that we made the first time. Now, if the police car or ambulance, though, moves, when it comes time to make the next wave, the next hey, hasn't the car itself traveled forward? So, when it comes time to make the next hey, instead of making it from back here, I've actually moved towards the back of the wave that I had propagated originally. So instead of standing from here to here, the distance between me and the person hearing it now is a little bit closer because now the car has moved forward. All right, so when it comes time to make the next wave, hey, so when it travels, I start here this time. Now, notice the spacing between the waves. The spacing between the waves now is much closer. I'm going to call this wavelength prime. This is the new wavelength, and it's shrunk a little bit because the new wave has climbed up on the back of the old wave, shortening the distance between the one I made originally and the new one that I'm making now, because the car itself has moved forward some distance. Now, the distance that the car moves forward, I'm going to call d sub s. The distance that it moves forward, that way. All right, so now let's take a look here and see what's actually happening. All right, the new wavelength, the wavelength that I get now, is going to be a little different. So the brand new wavelength is going to be equal to, we'll call that the total wavelength, or the final wavelength, whatever, is going to change. All right, now let's think about what this wavelength is, the new shorter version of it. If I took the distance from here to here, this original wavelength, this distance was, say, d, from there to there. Now I can subtract off the distance that the car moved forward, call that my little ds. Isn't that going to be the size or the length of the new wave? So this one has been shortened from the original one by the amount that the car has moved forward. And we're going to call that lambda prime. So we can now actually analyze, well, what is lambda prime? How has this actually affected the wavelength? And if the wavelength has changed, that also changes the frequency and the pitch of it. So if we look here, notice that the wavelength has actually gotten shorter, the spacing between the waves. So if we know this, the wavelength goes down, the frequency must have gone up. What does this person hear? It hears the new shortened waves, and they hear a higher pitch. So it's going to sound a little bit high in pitch. Instead of the old police car ambulance siren sound, it's going to sound a little higher pitch. People say, that's coming towards me, and that's the reason why it's so.